Hi everyone, my name is Yann Harel, and today with André and Basile Pinsard, we will tell you a bit more about our video game project, which consists in putting a Shinobi in the scanner. So more precisely, we developed and validated an fMRI and MEG compatible controller and gaming platform. So, video games are a type of highly promising experimental paradigms for neuroscience and artificial intelligence. Video game tasks are highly active. They are quite complex, but still controllable enough to be used in a laboratory settings. They allow us to get insights on the neural correlates of naturalistic behavior and cognition in complex environments. And they can be used also to leverage artificial intelligence techniques by offering a common ground to compare or benchmark human and artificial intelligence. You will learn more about this if you listen to Maximilien Leclay's or Aniruddha Kemtour's project. So an example of a video game used as an experimental paradigm is in this paper from Katsiri and collaborators, in which they use the video games called Busy Flag. It's a war game where you play a tank and you move around the map trying to find an opponent and destroy it. So their subjects were playing these video games in two conditions. In one condition, they thought that their opponent was a human, and the other condition, they thought that the opponent was a bot. But indeed, for both conditions, they were playing against a human in order to keep the difficulty constant. And so what's interesting in this study is that this paradigm led the researcher to produce brain activation maps that are characteristic to reward events. And these activation maps show differences between the two conditions. So video games can be used to actually implement a situation where we can derive meaningful activation maps. In this other study, Logan Cross and collaborators scanned humans during Atari games. So they use Pong, Enduro, and Space Invaders, which are quite old and simple Atari games, which can be played on a very simple response box, as it's normally used in fMRI and MEG studies. And the goal of that study was to actually map high-dimensional sensory inputs into actions, so based on what humans are doing during these games. The researchers developed a deep Q network to actually solve the game based on the pixel maps. They were able to correlate the predicted outputs from this network with the actual observed fMRI responses, as you can see on these activation maps. What's even more interesting is that they were able to use the different layers of the network to run a representational similarity analysis and correlate the representations in the various layers with the representation that can be identified from pixels, from a PCA, or from a variational autoencoder, showing various levels of abstractions in the hierarchy of the network. And again, the most interesting result in this study is the correlation between brain activity, for example, in the early visual, PPC, or motor regions, and these representations in the network. So they basically used a machine learning technique to model brain activity in a complex, in an ecological environment. So, as we've seen, using video games in neuroscience and machine learning research is promising, but it also comes with a lot of challenges. For example, the controller, the device that is used to play the game, is usually not compatible with most scanners, like MRI or MEG. Playing video game in a scanner will also lead to higher levels of motion artifacts, for example. And finally, a big problem with most video games that we would like to use is that they are usually closed source software, and that doesn't allow the researcher enough control to actually build an experiment from that. So to show an example of how heterogeneous the literature on video games can be, I made this small table where you can see that some studies used a response box, which is a very classical input device for MEG and MRI experiments. But some video games cannot be played with this kind of response box. For example, video games that require to move around in an environment are poorly suited for these kinds of devices. But you could use, for example, a joystick for that, like it was the case, for example, in the first study I told you about. The problem with that approach is that most devices that you will find won't be compatible, and so you will have to find a joystick that is very expensive and that will be specifically used in the scanner. And also, some researchers will even use fancier input devices depending on the video games that they want to play. So, for example, Anderson and collaborator with the game Space Fortress used a data glove in some experiments. So in order to solve these problems of heterogeneity between the input devices, we decided to design our own controller that will be fully based on optic fiber. And to tell you more about that, I will let my colleague André come in front of the camera.
Hello everyone, my name is André. I'm going to talk to you about the video game controller that we built for this project. So one of the first things that we obviously tried to do was to just take a regular commercial controller, open it and empty it of all its content. But one thing that we quickly realized was that there was a bunch of stuff built inside the shell itself, like a post for the screws or hardware to fix the electrical switch and everything, so that it was pretty hard to properly route all the fiber optics and the additional hardware that we needed inside the casing. So what that leads us to conclude was that it was probably better to go the long way about this and build our own version of the controller from scratch. So this is what we set to do. And to do this, we went through several design iterations on 3D modeling. The controller was entirely designed using Fusion 360. And for example, we went through iteration for the optical switches, which use fiber optics and mechanical shutter that just moves in front of two fibers to cut off light beam and detect a button press. So in this case, we show a design where all 4 switches are included into a single module versus the one that we end up with where switch are all individual module, self-contained, so that makes building, maintaining, repair a lot easier. We need to replace or change a switch. And if we look at the NL enclosure, the shape of the box itself, we went through several also design iteration, trying to find the most ergonomic shape. And you have an example here of what we started with and what we also ended up with. So when we set up to build our controller, we took all the design parts and had them manufactured using a 3D printer. Every part except the plastic screws were all 3D printed. After the part were printed out, we carefully assembled them into this controller here, everything including the buttons and even our little logo here. This was all carefully assembled and tested, and after we knew that everything worked, we were ready to play Shinobi inside the scanner. So here we have a participant who's inside the scanner, and we have that participant playing Shinobi here. That controller assembly, what it does is it communicates via fiber optics with an electronics module that's sitting inside the control room, and that module simulates a keyboard that is talking to the computer. That way we can interface it with the OpenAI Gym Retro.
So in order to run the video game, we will use the OpenAI Gym Retro library, which is a platform developed by OpenAI for reinforcement learning research. And the idea of that library is to allow the emulation of 9 different consoles and provide a Python environment to actually interact with the memory states of the game. So as a neuroscientist or machine learning researcher, this is exactly what we need in order to create experimental situations using video games. Gym Retro has integrated more than 1,000 games and also allows to easily integrate more games if we want to do an experiment on a game that's not provided with the library in its current state. Because Gym Retro comes with a GUI that allows the exploration of the memory states while we're playing. So using this tool, we can actually kind of reverse engineer the game in order to detect the memory addresses of relevant game variables, which is key in order to then use these variables in an experimental context. So in particular for our study, we chose the game Shinobi 3, Return of the Ninja Master, which is an action scrolling platformer. It's a simple game in which the goal is simply to reach the end of the level, but you will indeed encounter enemies or obstacles that you will need to get past. And at the end of the level, you will have to kill a boss, so a boss fight. The controls for this game are very simple. You can move left, move right. You sometimes have to move up or down, but most of the time you will only move left, right, and you will jump and hit with the right hand buttons. There is also a power up in the game, but our subjects were so skilled that they didn't have to use it, even if that was a possibility. And now I will let Basile present you the home and scanning setups.
Hi, I'm Basile. So now I'm going to present you the method for the acquisition of the data. So the participants were playing the game in 2 different setups. They were first trained at home on a small computer with the game pre-installed and that they connected to their own TV. They played with a SNES a commercial controller plugged with USB, and we didn't have any specific regimen for the training, and all the games were recorded on the computer, and we got them afterward. So we tracked the performance, and when they reached an asymptote on all the levels, they could proceed to the scanner, which is a second setup, which is, as you can see, more complex. We use in the scanner the MRI compatible controller that André described, and the rest of the setup, so the BioPack sensors, the sensimetric earbuds, the protection, and so you can imagine there was a period of adaptation to this new device, which is a bit bulkier, and also playing in a lying position, which is less ergonomic, and I guess nobody was used to play video game lying on the back. Now I'm going to present you what the dataset looks like, or will look like, because it's still ongoing its acquisition. So we asked the participant to train on the 3 different levels, which shared common mechanism for working, running, attacking, but also required to develop level-specific sequences of actions, such as hanging to or jumping between pipes in a certain level. And so in both setups, the software recording the game in the form of the initial state of the game and the key presses. So as these games are deterministic, there's no randomness in there, we can replay the execution of the game from this sparse data and get video frames, sound chunks, and also explore the memory state for variables of interest. like the life, the ammunition, the score, which sprite is being displayed, the enemy's position, etc. So this will result in 2 datasets that we are aiming to complete for the NeuroMod 2021 release. So we have 3 participants over the 6 which have already completed both the home acquisition and the acquisition in the scanner. And first, the behavioral dataset, so from data collected at home, will allow for the analysis of the learning process and also the acquisition and stabilization of the gameplay style that the player developed. And second, the fMRI dataset, in which each MRI series contained multiple repetitions of the 3 levels, which were looped over. So they play level 1, level 2, level 3, and again level 1, level 2, level 3. This repeatedly until a maximum length for each fMRI series. So the condition for the completion of participant acquisition was to reach 10 hours of usable gameplay data, and which roughly equals to 10 separate sessions of fMRI scanning, because like it's kind of an exhausting task, and after 1 hour you don't you want to stop in general. So Yann will continue to present the method used for the first analysis of the dataset.
So in order to validate the performance of our subjects in this video game, we used the game variables that were stored in the log files produced by the Gym Retro library, and we extracted 3 variables representing performance. So we were interested into the maximum score reached inside the repetition of a given level. We also looked at the percent of the level that was completed. So it was based on the proportion of the distance traveled by the player during this specific repetition of the level compared to the total length of the level. And we also looked at the health loss variable, which is indicative of how many times a player was hit by an enemy in the repetition. So we can see here the behavioral results for our subject 01. On this side, you can see the games that were played at home using the home scanners. And here on this graph, you can see a comparison of games, average the games that were played at home or in the scanners. So what we can see is that our player reached a plateau. Their performance increased until it reached a plateau, which is indicative that our player actually learned how to play the game. And this graph shows that the maximum score reached by the players were not lower in the scanner settings than at home. So it means that going from the at-home setup to the scanner didn't decrease the player's performance. And that's also something that we can observe using the percent complete variable. We can see that, again, the player reached a plateau and the performance was not diminished when going in the scanner. And again, with health loss, we can also find this pattern. The more games of training the subject had, and the less he was inclined to lose health during his repetition. And it's, again, this effect can be seen also on the scan sessions. So it's not limited to the home repetitions. Since there is a lot of motion artifacts during video game plays, we were really interested in looking at the frame-wise displacement values of our scanning sessions. As we can see in this graph, the results are pretty good. The data are convincingly clean of motion artifacts. Most of the values here that we can observe are below 0.5, which is a standard in neuroimaging, and we have very few outliers, as you can see here. So now let's take a look at the annotations that we were able to extract based on the logs files. First, we wanted to look indeed at all the actions performed by the player. But what's really powerful with Gym Retro is that we also have access to game events. So I mean by that events that are not triggered by the player, but that are really observed only by the player. So that's the case, for example, when the player loses a life. It's not necessarily linked to an action in particular, but it's linked to a punishment from the game. Using the jump event, we were able to build a general linear model and to regress the jump events from the brain signal. And what we can see here is that the sensory motor network that seemed to be activated when the player jumps is pretty consistent across sessions. So we can see here 7 different sessions. And every time, nearly every time, we can see the same patch of sensory and motor activity that is indicative of a specific network for this action. So now, if we take a look at a correlation between the different activation maps that were derived from this data, we can see that interestingly the jump and hit activation maps are pretty similar, which is quite expected because hit and jumps are both activation maps that are built based on an action event. So it was an action initiated by the subject. In contrast, the health loss activation maps were derived on an event that was not an action from the subject. So it's not surprising that hit and jump are more correlated because they both involve a movement of the thumb, while health loss doesn't. So here is what we can observe at the subject level. So when we combine all these activation maps of the 7 sessions together, we can see this sensory motor network becoming even more robust. And for health loss, we can also see a network that will be specific to that event, including sensory and even frontal regions. So to sum up a little bit all these informations, we collected brain data during the play sessions of a video game, which was a challenging task to do. We were able to do that thanks to an open designed fMRI and MEG compatible video game controller that we developed. And we validated this setup that also includes the Gym Retro library to allow us to emulate retro video game. We validated that using the video game Shinobi and producing a dataset of more than 10 hours of recordings per subject that were trained to play the game, so they were proficient at the game. And using this paradigm, we were able to actually derive activation maps that were meaningful and that can be interpretable. So the next steps for this project will be to start the data collection on the MEG setup, which is already ready to welcome our video game experiments. So now we're just gonna start the data collection. And we also intend to start collecting another video game, which is very famous. You may have heard about Super Mario Bros. What's really cool with this game is that we're gonna have a wide range of levels, 22 over the 32 levels of Super Mario Bros. compared to the 3 levels of Shinobi that we just had. It's going to be a great improvement. We're also aiming to collect about 10 hours per subject, both in MEG and fMRI, so 20 hours per subject in total, which is a lot of Super Mario Bros. Play. And Super Mario features 15 different enemies, 5 different Mario transformations, 5 types of collectibles, and as many opportunities to do some representational learning and all kinds of fancy machine learning techniques and neuroscientific tools. So thank you for listening, and I'm willing to answer any question you have.